Today we're going to talk about alternating series and the alternating series test for determining convergence of alternating series. So an alternating series is going to be a series whose terms alternate in sign, meaning our terms are going from positive to negative, and so on. Now, what we will see there whenever we see an alternating series in its general form in that summation notation is you're going to see some power of -1. It doesn't matter what it is. What it cannot be is like -1 to the 2n. That actually wouldn't be an alternating series because to the 2n power would mean that it's always an even power, which would always be positive. But as long as it's a power that is going to alternate back and forth, that -1 is your big clue. And they're not usually going to try to trick you like, this looks like an alternating series, but guess what? It's not. So that's a good clue of what you're looking for. Is that alternating piece the power of -1? Okay. Now, here is how we apply the alternating series test. So first off, when would you use the alternating series test? It's when you have a series that is flip-flopping back and forth. That's the first thing. So there's two parts. When you have an alternating series, as long as a sub n, meaning the non-negative part of it, we're just talking about this piece here, as long as that's greater than 0, then the alternating series converges if we meet both of the following conditions. Now, the two conditions are: 1, the limit as n approaches infinity of the a sub n term has to. What does that mean? This means that it fails the nth term test. Remember, the nth term test is for divergence. So if you get anything other than 0, the answer is it diverges. You're done. So it's definitely important to do that first. We have to make sure it doesn't diverge. Now, just because we get 0 does not guarantee that it's going to converge. What we have to make sure is the second condition, which essentially says that our terms are decreasing, okay? A sub n must be greater than a sub n plus 1. What that means is the term I'm on has to be bigger than the next term all the way down, okay? And so that, again, what we're looking for there is that the terms are decreasing. That's really what that says. Okay. So we want to decide whether these two series converge or diverge. So we're always going to start with step 1. And notice again, I want to make sure I point this out. We are only looking at a sub n. Again, a sub n does not include the alternating piece. So we're going to ignore the negative part in both of those cases. We're looking at the positive a sub n here. So let's look just at number 1 to start. So the first thing we're going to do is apply the nth term test. So we want the limit as n approaches infinity of, we ignore the alternating piece, 3n divided by 4n minus 1. Well, that's equal to 3/4, which is not equal to 0. That's what we need. So according to the nth term test, this series diverges. Diverges by nth term test. Okay, so that's all we got to do on that one. Pretty easy. So let's look at B. This one is the sum from 1 to infinity of -1 to the n plus 1 power over n. Now, again, it does not matter that this is an n plus 1 power. It's still going to alternate. So that's all that we care about. So we want to look first at our limit. The limit as n approaches infinity of 1 over n. That's what we're left with when we take the alternating piece out. And that does equal 0, which is the first thing that we want. So first condition is met. The second condition now is for us to compare the nth term, which is 1 over n. We want to compare that with the n plus first term. Okay. Now, it is true that this is greater than the next. And how do I know that? Well, if the denominators are bigger, then your fraction as a whole is actually smaller. So let's say that I had 2 for n. 1/2 is bigger than 1/3. 1/3 is smaller, even though the denominator is bigger. So this is definitely true. There's not much you need to show there other than making the statement that yes, this is true. If there's something glaringly obvious that it is not true, that's something you want to pay attention to. But typically, if you get past that first one, most of the time this is going to be the case. So we can then say that this series converges by the alternating series test. There is to it. So now, what is unique about alternating series is we can consider a couple of different things as a result. What is unique about an alternating series is that we can use partial sums to estimate pretty precisely what the actual sum is, okay? And anytime we use an approximation strategy, it's only any good if we can know exactly how accurate that estimation is. And so that leads us to this concept of the error bound, which we're going to talk about today. The second thing is absolute convergence versus conditional convergence. Does this series only converge because it has negatives in it, or would it converge regardless of the negatives? We're going to look at that in the next video. So for today, let's finish up by talking about the remainder. All right, for a convergent alternating series, the partial sum S sub n can be useful in approximating the actual sum S for the series. So we're going to use a little bit of notation here. We're going to call the error, like how far is our approximation from the actual sum? We're going to call that R sub n and call that the remainder. So R sub n then, does it make sense, is going to be S minus S sub n, the actual sum minus the sum that we use to estimate how far apart they are. That's going to be the remainder. So if a convergent alternating series satisfies the conditions of the alternating series test, then the error for the nth partial sum is less than the a sub n plus 1 term. Now notice that's not a sum, that's not the n plus first sum, that's just the n plus first term, and it's going to have the same sign as the first unused term. So what that says is that the absolute value of the remainder is less than or equal to the value of the next term. So let's look at example 5. It says use the first 5 terms to approximate the series and determine the error bound. So the first thing that we are going to have to do is look at those first 5 terms so that we can find the 5th partial sum. So we're going to start by finding S5. We're going to do -1 to the first divided by 1 plus -1 to the second divided by 2 plus -1 to the third divided by 3 plus -1 to the fourth divided by 4 plus -1 to the fifth divided by 5. Well, this comes out to -1 plus 1/2 minus 1/3 plus 1/4 minus 1/5. You can see the alternating of terms happening there. This comes out to approximately negative 0.783. Now, the other thing that is important to know, we are looking at the 5th partial sum, so we need to consider the 6th term of the sequence. So the 6th term would be -1 to the 6th over 6th, which is 1/6. So our error, our remainder, is less than 1/6 from what the actual sum of the series is going to be. Now here's how we determine the error bound. The error bound is an interval, So we have an upper bound and a lower bound of where we know that our actual sum resides. So the rule is that the remainder, which is the absolute value of the sum minus the partial sum, I shouldn't put n there because in this case, it's going to be 5. We know that that has to be less than or equal to 1/6. Well, using what we know about absolute value, that means we can say that negative 1/6 is less than or equal to S minus, now we know this number here, negative 0.783. So really this will be plus 0.783 is less than or equal to 1/6. Now, if we subtract 0.783 from all sides, we get negative 0.950 is less than or equal to S is less than or equal to negative 0.616. This is our error bound. And what that tells us is whatever the sum is, it is within this interval. Now I could make this error bound smaller and smaller by using more and more terms. The more terms we get, the more accurate our partial sum estimation is going to be. So B says, based on your results from the first 5 terms and the error bound, is it possible that this sum is equal to the natural log of 3 divided by 2? Well, if you evaluate the natural log of 3 divided by 2, that's approximately 0.549. So could this be the sum of our series? No, because we know what the error bound, we know where it is supposed to be. So the answer is no, natural log of 3 over 2 is outside of the error bound. Okay. C says, find the sum of the series accurate to 3 decimal places. Now, this means that we need an error less than 0.001, okay? So here's what we know. We know this is how C is different from A. Part A said use 5 terms to approximate it and then determine what the error is using that sum. We're saying this is the error I want. How many terms do I need? So we're solving for N in this case. So what we know, we have to gather some information here. We know that the A sub N plus 1 term for this series is 1 over N plus 1. That's what we're plugging in here for, we're replacing that with N plus 1. And we're going to ignore the alternating part for now. What we want, we know that the absolute value of our remainder has to be less than or equal to 1 over N plus 1. And we want that to be less than 0.001. So really, all we have to concern ourselves with then is this right here. We need an N that makes this inequality true. Well, 1 over N plus 1 is less than 0.001 is 1/1000th. And so if we cross multiply here, then we get 1000 is less than N plus 1. So that means N has to be more than 999. That tells us that we need at least 999 terms. Okay, so it asked us to go ahead and find the sum. Now you're not going to add up 999 terms by hand. Our graphing calculator can do this for us. So we want the sum from 1 to 999 of negative 1 to the N plus 1 over N. In your graphing calculators, as long as you have one of the newer versions, it's going to be math 0. and I'm sure you can figure out how to set it up from there once you get there. If you have an older model of calculator, it's a little more convoluted than that, and I will post a link on Canvas with the instructions, a quick Google search or a YouTube tutorial for how to evaluate a series on a TI-83 will find you what you need, but I will post my information as well. So that is the idea. You're going to do very similar on examples A and B on the next page. All this one is asking us is to find the number of terms. Now, today is February 25th, 2021. If that is your school year, then you don't have these examples in your notes, but these are some good extra ones to take a peek at real quick to see if you understand this. So maybe pause the video and in the margin somewhere, see if you can determine for part A, the number of terms that you would need to approximate the sum with an error less than 0.001. And I'll come back with the answers in just a second so you can check. All right, on this one, we get a decimal when we solve for n. We get 4.623. So we can only have whole numbers of terms. So that tells us that we need at least 5 terms. We're just going to bounce up to the next one. And so that is how we can evaluate that.